And let me also give all of you guys permission. All right. All right. Yeah, I wanted to say a few words about sheaves and scats. Today, I guess it will be mostly sheaves before we can talk about scats. Um, and let's recall what we did last time. We defined, well, not really last time, but a couple of lectures before that, we defined a smooth set F as a pre-sheaf. So you guys can see my screen and my pointer, right?
Mm-hmm.
Okay. Is a pre-sheaf of sets on the side of Cartesian spaces. And the way you should think about this is that the value of this pre-sheaf on some Cartesian space U is the set of smooth functions from U to the space represented by F. And we also discussed how to make this perfectly rigorous. Through the United lemma, you can make U into a representable pre-sheaf. And then this statement becomes literally that f of u is a set of morphisms from the representable pre-sheaf on U to F. However, the notion of a pre-sheaf does not exhaust all what we need from a smooth set. And in particular, consider the following situation where we have a space X. Here's, oops. And how do I, oh no. I think I figured out what's happening. Every time I turn off and on my my tablet, somehow the application loses track. So let me track it down for a second. I've already opened it. Let me reshare it with you guys.
Sorry, please, can you give me again permission for recording since I can't record? I don't know why.
Okay, just a second. Okay, you guys should now all be able to record.
Thank you.
And let me reshare the screen again. I think I finally should be able. Yes, finally I can write. And now, of course, I have to read. And of course, I can change the pages. Okay, so finally we can proceed. All right, so let's imagine here's our X, which is covered by two open sets. I guess red and green. The green one is U. Okay, this is ridiculous. And the red one is V. And the intersection, I guess red plus green equals yellow. Uh, the intersection is U intersect V. And let's say we have some smooth set. Then we can talk about smooth maps from X to F. So F is our smooth set. And we can also talk about smooth maps from individual uh, from individual elements of the open cover, U and V. And if we take a smooth map from X to F and restrict it to U and to V, the resulting maps from U and V are not independent. They must coincide on the intersection. And this is what I indicated here using a fiber product. So the fiber product here is the set of all pairs given by a smooth map from U to F and a smooth map from V to F that coincide on the intersection of U and V. So this is what is known as a compatible family. Conveniently, I can use the same color to talk about compatibility condition. And the sheaf condition in its easiest formulation simply states that this map that takes a smooth map from X to F and produces out of it a compatible family with respect to U and V is an isomorphism from the set of smooth maps from X to F to the set of compatible families. That is to say, if you have a smooth map from U to F and a smooth map from V to F, and they coincide on the intersection, there is exactly one smooth map from the union of U and V, which is X, into F, whose restrictions to U and V coincide with the given maps. And this condition is not always satisfied. And just to give you one sort of maybe elementary counterexample, consider the pre-sheaf that to a Cartesian space or a manifold X assigns the set of, say, smooth functions f, which are either non-negative or non-positive. This is a pre-sheaf because if you have such a smooth function, you can precompose it with another map from x prime to x, and you get also a non-negative or a non-positive function. But it's not a sheaf because this condition is not satisfied. We can write down a positive function on U, a negative function on V, and on the intersection, this function will vanish. It will be zero on the intersection. And this will be a compatible family, right? So you have a positive function on U and a negative function on V, which are elements of this pre-sheaf. They coincide on the intersection where they're both equal to zero. And therefore, they form a compatible family. But of course, this compatible family does not glue to a true section over X, simply because over X it would have to be both positive and negative. And that's exactly what we don't allow here. So there are certainly many examples of pre-sheaves that are not sheaves. So in our definition of a sheaf, we require this restriction map that sends a section over X to a compatible family to be an isomorphism. So that's part of a definition of a smooth set. Any questions so far?
So this definition is more general than diffeological space?
Yes, in fact, diffeological space is what is known as a concrete smooth set.
Mm-hmm.
The concreteness condition, I mean, is just in my mind, a crutch to sort of
Force
help
it to have a
you
set of points.
accommodate the usual conception. Yeah, it's like a space is somehow determined by its points, which at this stage we really should consider as a harmful idea
Mm-hmm.
because it doesn't really allow you to do anything, but it does prevent you from doing many things. But I will talk a bit more about points, maybe just a bit later.
Okay, right. So
But
So
otherwise,
we'll talk about the concreteness condition at the right time.
yeah. I mean, in a sense, most smooth sets will be diffeological spaces, except for exotic objects like differential forms. These are not concrete.
Right. So is the concreteness condition essentially the embedding of smooth manifolds in the category of smooth spaces, or does this already take care of that by smooth manifolds being
Smooth manifolds will be, when you turn them into smooth sets, they happen to be concrete. Yes.
right? Right, but they're a subcategory of concrete spaces already, so
Yeah, they form, in fact, a full subcategory.
full subcategory. Yeah.
Yeah.
Okay. Thanks.
You're welcome. All right, so let me repeat the definition of a sheaf in a sort of slightly more formal way. So a pre-sheaf is a sheaf if for any object in our psych, in our case that's the Cartesian spaces, and for any open cover of this object, which we call UI here. This open cover can be indexed by an arbitrary set, capital I. So UI is an open subset of X. And here, since we were talking previously all about Cartesian spaces and not just smooth manifolds in general, you can say, in fact, that UI is a Cartesian space, and moreover, the intersections UI and UJ are also Cartesian spaces. And this is known as what is sometimes called a good cover. Meaning an open cover where all elements are diffeomorphic to Cartesian spaces and their finite intersections are also diffeomorphic to Cartesian spaces. And you may ask, well, what about other open covers? Should we not also say something about them? But fortunately for us, it's not necessary to do so because any open cover can be refined by a good open cover, meaning we can find some other good open cover, and any element in this good open cover is a subset of some element of the open cover that was originally given to us. So the sheaf condition for arbitrary good open covers will imply the sheaf condition for arbitrary open covers. That's why it's perfectly safe here to assume we have a good cover. And let's more formally say mention the sheaf condition and the notion of a compatible family. So in general, when our open cover has more than one element, the resulting family of elements will be indexed by the set capital I. And for every such element, we have a section, a smooth map, if you want, from UI to F. And we also have to say something about the intersections. So the intersections will be indexed by a pair of indices, J and K. So for all, yeah, I guess this was moved at some point. So, for all J and K, you have a smooth map, if you want, from UJ intersect UK to F. And there are true maps you can write down from the gauger that defines a family of sections over UI to the gauger of the restrictions to the intersections. And the point here is that you can either restrict from UJ or you can restrict from UK. But a bit more formally, to define a pair of maps from this product here on the left to this product here on the right, I'm going to define their individual components. So by the universal property of products, it suffices to define individual components of such maps indexed by some pair JK. So that's what I denoted by the blue arrow. So the blue arrow is a projection map. And it suffices to specify such projection components for all J and K. So
And
what is
sorry,
this map?
Dmitri.
Yeah.
Sorry. Oh.
Go ahead.
Oh, no, I was just wondering why we're, I may probably this will be answered soon enough, but why we're including the projection maps in the data of this diagram?
It's not included in the Geiger. It's not included in the Geiger. It's just we are explaining what the maps are.
Okay. Okay.
Yeah, so the blue stuff is auxiliary, it just shows you what the maps are. Yeah. Yeah,
Gotcha.
so you really should be ignoring the blue stuff once you understand the true horizontal maps.
Right. Okay. Right. The equalizer part of it.
Mm-hmm.
I mean, the equalizer fork. I mean, the whole fork.
Yeah. So we are defining the component with index J, K. And such a component, which lands in this set f of u, j intersect uk here, there are two ways to define it. Either you can start here, project to f of uj, and then further restrict to the double intersection. Or you can start in the product, project to uk first, and then restrict to the intersection. And these are the two components we were trying to define. So the blue scuff explains how the horizontal maps work. So a formal way to say it is that the diagrams, the squares on top and bottom are commutative. And this map here on the left, from f of x to the product, well, again, we have to specify its individual components. So I have to specify for you a map from f of x to f of ui. And this will simply be a restriction map. So again, ui, recall, is an open subset of x. So the structure map of a pre-sheaf associated to the inclusion of ui into x will give you a restriction map. Now we can say exactly what it means to be a compatible family. A compatible family will be an element in this product such that when you map it using those two arrows to the product on the right, you will have you will get the same elements. In perhaps less formal and less diagrammatic way, an element in this product will be a family of sections. Let's see, it gives them a name actually. Yeah, I didn't even bother giving them a name, but let me just say it in words. So here, an element will be a family of sections. Maybe actually here's blue. Fi goes from ui to f for all I. And such a family can be mapped by those true maps into two families here indexed by j and k. The first one will be f j restricted to uj intersect uk, and the second one will be f k restricted to uj intersected with uk. And so the requirement that the for a family here to be compatible, its images under these two arrows must be the same, amounts to saying that these two restrictions are equal. So fj and fk coincide when we restrict them to the intersection of uj and uk. So this is just a fancy version of the condition on the previous page that is still present. Oops. All right. I always struggle in this app to move. This is erase, draw, erase, select. Yeah, maybe I should finally switch to a better app. I mean, this is just too bad. Yeah, so the condition here is just a fancy multi-index version of what we said here, maybe somewhat informally. In particular, notice like if your capital I only has two elements, then you will see precisely this condition here. Because if capital I has two elements, and maybe this was something I should have indicated maybe. Let me in fact insert a page. So in the case capital I has two elements, we will get a map from fx to f of u1 times f of u2. Then we'll have two maps to f of u1 intersect u2. And I guess the way I formulated it, I should have probably mentioned that it's perfectly fine here to impose a restriction that j is smaller than k. It's optional. You can impose it or not, and in both cases, the result will be the same. You will get the same condition. And now, if you look carefully, so you have a pair of sections here, let's say f1, f2. f1 is a section over u1, and f2 is a section over u2. And then their images under these, the image of this pair under the first map will be f1 restricted to u1 intersect u2. Sorry, what am I saying? Yeah, no, this is correct. u1 intersect u2. And the second map will map it to f2 intersect u1 intersect u2. So the two must be the same. So you see how the fancy condition for many open sets recovers the simple condition that we talked about previously here. Oh yeah, and I should have mentioned it more explicitly. So we said what a compatible family is. So a compatible family is an element in the set that maps to the same element by both of these arrows. And then the actual definition of a sheaf says the map from f of x to compatible families is a bijection. And an elegant categorical way to say this is to say that this map here, this arrow, is the equalizer arrow of these two arrows. What it means is that it satisfies a universal property, but in a more sort of hands-on way, you can say that you have a map from f of x to this product, and you know that the composition of this arrow here with these two arrows gives you the same arrow from f of x to the giant product here. Then you know that the map from f of x factors through the set of compatible families here, which is the set where the two maps coincide. And being an equalizer arrow simply means that this map from f of x to the set of compatible families is a bijection. So f of x is precisely the same as the set of all compatible families. So the green arrow being an equalizer is precisely the sheaf condition. Maybe I should have finished it, yes. So the green arrow All right, any questions before we move on to examples? All right, let's do some
Right.
examples. Yeah.
Products when we're writing product in the
Yeah, just a second, let me move back. Yes.
equalizer fork are
Sorry, you're going in and out. Your connection is unstable. Could you repeat?
appearing in the equalizer fork and below are fiber products.
In the equalizer fork, so these are ordinary categorical products here. The fiber product, if you take the equalizer of these two arrows here, the equalizer of these two arrows here, which would be a map like this. Right, so capital E is a set of all compatible families. Then this capital E, in a sense, E is a certain generalized fiber product, right? It's not a fiber product in the usual sense, but it has more components to it, right? And of course, in the case of true open sets, it would reduce to this fiber product here. But in general, it will have more than one element, more than one factor.
Construct equalizers.
Sorry, your connection is still unstable. Could you repeat?
Yeah, sorry. It might be my microphone. Equalizers given products and pullbacks.
Yeah, I mean, this, in a sense, this formula explains you
Generalized.
how to compute the equalizer using, like equalizers and fiber products can be expressed through each other, and basically here you see what is happening. Yeah. I think your problem, James, maybe there's some background noise, and Zoom doesn't know how to distinguish between the background noise and your voice, and that's why your voice always comes through like maybe a big with a delay, and I only hear the last parts of your phrases. All right, more questions? All right, let's move on to examples where the sheaf property is satisfied or not. And of course, our favorite example is giving a smooth manifold M. I can turn it into a smooth set by sending a Cartesian space U to the set of smooth maps from U to M. So why is this a sheaf? Well, according to the here, the property we mentioned here on the left, we would have to show that the restriction map from, so imagining on a scale of F, you have the actual M. So we need to show that smooth maps from X to M are the same as compatible pairs, a smooth map from U to M and a smooth map from V to M that coincide on U-intercept V. And maybe the first thing to notice here is that if you have such a compatible pair, then it secondly gives rise to a unique map of sets, from X to M, And the only thing essentially that we have to do is to show that this map from X to M that results from gluing these two guys is smooth. But smoothness is a local property. To check that a function is smooth, it suffices to show that it's smooth on every element of some open cover, such as, for example, the open cover consisting of U and V. And once you restrict to U and V, you get the existing components in this fiber product, which you know to be smooth by assumption. So the only property of smooth functions that we use here is that smoothness can be checked locally on an open cover. Okay. Next, we can perhaps talk a bit about our favorite example, the smooth set of all smooth maps from one smooth manifold M to another smooth manifold N. And let's recall how we defined this as a smooth set. We said we send U to the set of smooth maps from U times M to N. And we spent a lot of time motivating this definition. Basically, it's the usual home product adjunction for sets, which you now say, okay, I want to have the same property for smooth sets. And essentially, we build it in by definition. Why is this a sheaf? Let me maybe spend some time explaining the sheaf property. So the sheaf property here would be saying that in the situation of this example on the left with X, U, and V, we would evaluate our pre-sheaves on X, U, V, and their intersection. And we would have to show that the induced map from X times M to N to the fiber product is a bijection. Let's look more closely at this fiber product and the restriction map. If you look more closely, you see that U times M and V times M form an open cover of X times M. And their intersection, the intersection of U times M and V times M, will be precisely this intersection here. In other words, what we see here is a special case of the compatible family for the open cover of X times M by U times M and V times M.
In what cases we can do this? take times and construct such map? In what case?
Yeah, I mean,
What
basically
condition we need?
it works, for example, for any site with finite products. If your site has finite products, then this trick is going to work. And in fact, even if it doesn't have finite products, it's still going to work. You just have to say a bit more. Yeah. So basically, it always works. So here, U times M, V times M is an open cover.
It works well for any site, yes? As I understand.
Yeah, pretty much. Yeah. This is how you can define internal home for pre-sheaves on any site. Yeah. Yeah, so there's nothing real particularly specific to smooth manifolds here.
And also smooth map we also can take in such a way, yes, when times of smooth maps as on the right, yes, in the same conditions.
So on the right, we have smooth maps, and what is the question?
About when we can take this equations, yes, this condition. In which conditions we need to imply?
Yeah, it's the same. Like the point is that the condition of the gluing, I should have probably mentioned words like gluing property or design property. Yeah, let me write it here. Or descent property. Yeah, so the point is that we just demonstrated that the gluing property for this sheaf here, as we revealed, is precisely the gluing property for the representable sheaf of capital N, or rather the sheaf associated to the manifold capital N, but with respect to an open cover given by taking the product with capital M. So in fact, the sheaf property of this internal home reduces to the sheaf property of the previous example here, which we also explain how to prove.
Okay, thank you.
Mm-hmm. Then the more exotic examples, like for example, differential forms. If you recall, we talked a bit about differential forms as a smooth set. You send U to the set of smooth differential N forms on U. That's also a sheaf because once again, differential forms, their smoothness can be checked locally on an open cover in a precisely the same manner as usual. Similarly, closed forms. Being a closed form means the Durham differential vanishes, and that's again a local property. And finally, the sheaf of the pre-sheaf of Riemannian metrics that sends U to the set of Riemannian metrics on U. That's a pre-sheaf because Riemannian metrics can be restricted along open embeddings. And it is also a sheaf, again, for essentially the same reason, because a Riemannian metric is, by definition, if you want, a section of the second symmetric power of the cotangent fungal. and that's being a smooth section is once again a local condition. Okay. Any questions so far?
Please, can you repeat about D map?
D map, sorry, which map?
Where we consider Riemann.
Yeah, so for Riemann metrics on a, let's see if I have any space. The point is like Riemann metrics on some U, that's by definition, smooth sections of the second symmetric power of the cotangent bundle of U.
Yeah, thank you.
Yeah, so being such a smooth section is again a local property. Yeah. All right, let's do some non-examples. Well, very good one of them, right? Where we say positive or negative functions. That's a pre-sheaf, but not a sheaf, because even if you are locally either positive or negative, that doesn't mean you are globally positive or negative, as you can see from this example, that you can be positive on U and negative on V and vanish on the intersection. But then when you have the union of U and V, you will be both positive and negative, and that violates the gluing property. Another example in a sort of similar spirit is the set of all thank U to the set of all bounded smooth functions from U to real numbers, for example. And again, this has a this is not a pre-sheaf because we can restrict a bounded function to a bounded function. But it's not a sheaf because the gluing property will be violated. And in this case, we can actually see that it's necessary to have more than one open set in a cover, more than two open sets in a cover, because this pre-sheaf here, it satisfies the gluing property for open covers with true elements, but not open covers with infinite covers. Why does it satisfy the gluing property for covers with true elements? Well, if you have a bounded function on U and a bounded function on V, the function, the gluing to U union V will also be bounded simply because you can take the a maximum of the true individual bounds, and this will be a bound on the whole union. So for two element covers is just fine. The same trick also works for finite covers. But for an infinite cover, this trick is not going to work because the maximum of an infinite family of numbers need not exist. Right? The family of numbers itself can be unbounded. And you can easily construct examples using, say, partitions of unity, where this property will be violated. In fact, let me maybe sort of try to give you an indication. Here's a picture. I have some function here, some bigger function here, even bigger function here, even bigger function here, and they grow indefinitely. So if you pick an open cover, we're using those colored intervals like I indicated here. Then you will see a compatible family. Restricted to each individual open set, your function will be bounded. But when you try to glue them on the whole real line, you will see an unbounded function. So that's an example of a pre-sheaf that satisfies a gluing condition for open covers with two elements, but does not satisfy for open covers with infinitely many elements. Which I hope shows to you that I perhaps did not waste your time when I talked about the more general version here. So this version is indeed, this abstract version for infinitely many open sets is indeed more general than the version for just two open sets that we presented here on the left.
Please, can you repeat why it is violated based on this picture?
Yeah, so here we have an example of a compatible family that does not admit a gluing, because its gluing would have to be a smooth function defined on the whole real line. So these are graphs of functions, graphs of these sections Fi. So we have a compatible family, and when restricted to an individual open set in the family, each Fi will be a bounded function. It is bounded because the interval has a finite length, and on a compact interval, a continuous function is bounded. But when we take the gluing of this family, so the gluing exists as a smooth function, as an unbounded smooth function. And if you now you can observe that the gluing as a smooth function will not be bounded, because as you move from left to right, your functions get bigger and bigger values. So the gluing is a smooth function which is not bounded. And then we also have a question in chat, this set of sections in point D. So this is talking about the example with Riemannian metrics. Is not exactly Riemannian metrics, but possibly degenerate pseudo-Riemannian ones, right? Well, here we do not restrict along arbitrary smooth maps, but we only restrict along open embeddings, right? So if you may recall, Oh yeah, sorry, as a sheaf. Yeah, I guess I was thinking already about the next page where I talk about a cow. Yeah, no, that's right. I mean, I shouldn't call them Riemannian metrics. I should call them, degenerate. Plus degenerate metrics, yes. Yeah, and continuing our examples in the same spirit, you can also see that, say, if you send U to the set of all functions from U to R, not necessarily smooth, just arbitrary functions, such as their support, the place where they're non-vanishing, is a finite set. So basically, skyscraper functions. This will also be an example of a pre-sheaf that is not a sheaf, but it does satisfy the gluing property for finite covers. And as another possibly instructive example of a pre-sheaf that is not a sheaf, we can maybe cite the example of exact differential forms, except that unfortunately on Cartesian spaces there is no difference between exact forms and closed forms. By Poincaré lemma tells you that any exact form, any closed form on a Cartesian space is exact. So if we are to make use of this example, we would have to switch to the side of all smooth manifolds and not just Cartesian spaces. And indeed, on arbitrary smooth manifolds, there are exact forms. There are closed forms that are not exact. So these two pre-sheaves will no longer be the same. And exact forms form a pre-sheaf, but this pre-sheaf will not be a sheaf because if you have a compatible family of exact forms, is going to glue to a form, a smooth form, which in fact will be closed, but it will not be exact. And I encourage you to write down maybe a simple counterexample on the, so the simplest possible counterexample will be on, say, C cross the punctured complex plane, where you have a form dz over z, which is locally exact, but it's not globally exact. And therefore, this form gives you an example that violates the gluing property. You have a form whose restriction to some open cover will be exact forms, which will form a compatible family, which does not glue to an exact form because it glues to a form that is closed but not exact. All right. Any questions about examples, or perhaps we want to see even more examples, or perhaps you have questions, maybe you know some pre-sheaf and
Please, can you review more about gluing of forms? Can you please draw a picture as in the first example, if you don't mind?
you mean the very last example?
Yes.
Yeah, we can say a bit more, yes. So on C cross, you have a form called dz over z. Well, z is x plus I times y. Dz is, so I should have said dz. I guess, no, I think it's fine. Let's see. No, it's fine. dz is dx plus I dy. This form is closed, right? We can compute this differential. So when we compute this differential, we'll see, well, how do you compute the differential of a one form times some smooth function, which in this case is 1 over x plus iy? Well, you would take the differential of the smooth function, and you would take the partial derivatives. Well, here we only need one partial derivative with respect to the other variable, because the partial derivative with respect to x will give you dx, which will be annihilated by the dx, so only dy survives. So what you get will be, well, let me write it as an intermediate step. And here the differential would be partial derivatives. So let me write it down. Wedge dx plus a totally similar expression for dy. Not totally similar, but exactly the same. And then you see how this dx will be annihilated by this dx here. So what remains will be dy wedge this dx plus dx wedge this dy, and dy dx equals negative dx dy. So altogether we see negative partial derivative plus and times dx dy. Oops. This is what I don't get. Somehow suddenly I was writing and oh yeah, I think it's the scroll bar here. And now we can observe that these two guys are, this function here is 0, right? Because, I mean, you can differentiate with respect to y. So what you get when you differentiate with respect to y, you see negative one times x plus iy squared times the derivative with respect to y, which will be I, and same story here. Do we get 0? No, we don't get 0. I think I forgot to put a bar somewhere. Maybe here. Oh, yeah, so I forgot to put I here. What? Sorry about that. Let's see. Yep, and now we can see 0. So this form is closed. And now I have to insert yet another page. So this form is closed. We just check computing is differential and C is equal to 0. But it's not exact. How do we know it's not exact? We integrate this form over is not exact on, let's say, on C cross. So we integrate it over, say, some closed submanifold inside C cross. For example, we can integrate it over a circle, right? The circle is parameterized by sending t to so z equals exponent of it, where t ranges from 0 to 2 pi. And then dz will be, so from 0 to 2 pi, dz will be the derivative of this function with respect to t. So that will be I times the exponent of it dt over z, which is exponent of it. And these two guys cancel each other, and you see 2 pi I. So we demonstrated that this form cannot possibly be exact because by the Stokes theorem, the integral of an exact form would have to be 0. Since it's non-zero here, it's not exact. But nevertheless, a closed form will be exact on every subset of C cross, which is diffeomorphic to a Cartesian subspace, right? If U is a subset of C cross, and U is diffeomorphic to R2, then the restriction of dz over z to U is exact by Poincaré lemma. Let's see what happened. The left side is moving, but the right side is no longer moving. Oh, okay. What? Right, so the Poincaré lemma says on R2, any closed form is exact. And the restriction of a closed form is always closed. So now you can see where this is going. I'm going to cover C cross by two open sets, both of which will be diffeomorphic to R2, and their intersection will be diffeomorphic, I guess, to two disjoint copies of R2. So the first one will be C minus the negative real line, and the second one will be C minus the positive real line. Right, so geometrically these would look like, well, take a complex plane, cut out this line, and take everything else. That's U. And likewise cut out the other axis, and that's V. Then U intersect V will be C without the whole real line. So these two guys, by the way, are diffeomorphic to R2. And these guys are diffeomorphic to two copies of R2. And from each of those three sets, the restriction of dz over z will be an exact form. So you see you have a compatible family of exact forms on the open cover U and V, but they glue to some smooth form dz over z, which is closed but not exact. So this formally proves that exact forms don't form a sheaf, which is, of course, a simple incarnation of the Gram cohomology.
Thank you very much for clear and detailed explanation.
All right, any more questions? Let me now jump from this extremely concrete example to a sort of big picture. What is this? Let me now jump from this extremely concrete example to a much more abstract example of or a situation. So the question I want to address is, you may have heard about sheaves in like sheaf cohomology and similar settings. And the sheaves on Cartesian spaces that we considered so far don't seem to have anything to do with sheaves you may have seen in like more traditional sheaf cohomology and the like. Like in algebraic geometry, you would almost immediately define sheaves. However, it's basically an artifact of using somewhat different sites. And more formally, we have two important dichotomies to consider when we talk about sheaves. And the first dichotomy is about morphisms in your site that you allow as morphisms as your site. In our case, we had Cartesian spaces, or perhaps some analogs like affine schemes or affine C infinity schemes. And we did allow arbitrary maps between such arbitrary smooth maps, or we didn't place any serious restrictions on those maps. And we saw how sheaves on such sites, like Cartesian spaces, are in some sense generalized spaces. For example, smooth sets. Or for affine schemes, you will see something called an algebraic space, which in particular includes schemes and other objects. Smooth sets, or in the algebraic geometry settings, you have algebraic spaces. But there is another alternative, which is to use maps that look like maybe open embeddings or similar type of maps. For example, you can consider Cartesian spaces and their open embeddings. Perhaps you can even restrict to Cartesian spaces of a fixed dimension D. Or perhaps you can consider affine schemes and their open immersions. And this is a legitimate alternative to the site that we considered previously. And you can also consider sheaves on such sites where morphisms now have this very restricted nature. And it turns out that sheaves will behave or have a flavor of generalized manifolds. And what I mean by manifolds is basically here I mean just objects that locally look like objects in your original site. For example, objects that locally look like d-dimensional manifolds, or objects that locally look like an affine scheme. So what falls under this paradigm would be, for example, for Cartesian manifolds, you would see manifolds, and more generally orbifolds. So orbifolds, if you know what that is, it's something locally looks like a quotient of a Cartesian space, and quotients will be handled by the formalism of pre-sheaves. So in fact, in our understanding, that amounts to saying that an orbifold locally looks like a Cartesian space. And more generally, something called an étal stack will also be an example. In algebraic geometry, schemes, for example, are defined as something that locally looks like an affine scheme. So this dichotomy is, in algebraic geometry at least, is referred to as Petit versus Gros site. The Petit topos. Petit simply means small, and Gros, of course, means large. Okay, so that's one important dichotomy. So taking arbitrary maps in your site produces something like a generalized space, which can be, in some sense, infinite dimensional. For example, smooth sets can be something like hom from M to N, whereas restricting your morphisms in your site to something like open embeddings or open immersions or similar type of maps produces a notion of a generalized manifold, which is much more restrictive, and objects here are going to look locally like objects in your site. So no more, you do not have, for example, infinite dimensional mapping spaces anymore. Okay, so that's the first important dichotomy, Petit versus Gros topos. And there's another important dichotomy which is relevant to what we previously mentioned about sheaves in algebraic geometry. And this dichotomy is, perhaps I can call it somewhat less standard, absolute versus relative dichotomy. In the absolute setting, your psych, its objects are just spaces in the usual sense, like Cartesian spaces, affine schemes, d-dimensional manifolds, and their open embeddings. And in the relative case, objects in your psych will be spaces equipped with a map to a fixed space X, where X can be, say, an object in your psych itself, or more generally, it can be a sheaf on your psych. So what's the difference between these two sites? Well, sheaves on the in the absolute setting is something we already talked about. They will be generalized spaces or generalized manifolds, whereas sheaves in the relative setting, when your objects in your psych are equipped with a map to X, these sheaves will be some kind of generalized spaces with a map to X, or perhaps a generalized manifold with some kind of a Cal map or open embedding or a similar local homeomorphism to X. And this relative setting is what you use when you define traditional sheaves on a topological space, which is an example I will consider in a second. But let me first here is sort of maybe a nice little table summarizing what you have so far. We have Grow versus Pti. So in the Grow topos, morphisms will be arbitrary maps from U to V. And in the Pti topos, morphisms will be something like some kind of open embedding or local homeomorphism or an Cal map from U to V. And in the absolute setting, that's it. But in the relative setting, you also have a map to X, where X is an object in your psych or perhaps a sheaf on your psych. So in the grow relative setting, you will have like an object in your psych is a map from U to X, and the morphism in your psych will be a commutative triangle. And in the Pti relative setting, you will have like objects in your psych will be, say, open embeddings from U into X. And morphisms between two such objects will be a commutative triangle of open embeddings.
Quick, what
Uh-huh.
are there special conditions needed to relate a fixed space to, you know, the probes into that space as an object within some grow site, like logical spaces?
Sorry, say again. You are constantly interrupting because somehow your background noise interferes with the. I think you.
I don't know what it is. There's no background noise. I mean, I'm in a totally silent room.
That's really strange because I somehow do hear. You know what? Maybe in your audio settings, you should go into your audio settings and turn off background noise suppression if it is turned on. Because that could be interfering with what you're saying. So what was the question again? Now we don't hear you at all, I think.
I typed my question. So
Okay, if the growth cycle may be related to the petit cycle via the quotient, well, I mean, of course, the petit cycle includes in the growth cycle, which of course can be used to construct various comparison functors. So this inclusion, of course, is basically saying you that manifolds and open embeddings of manifolds include into generalized spaces, or more precisely, étal stacks include into generalized spaces, which is a fairly well-known inclusion. So yeah, absolutely, you can relate it. Yeah, the petit stuff usually includes in the growth stuff. In a sense, this works. Yeah, I mean, it works in a lot of abstraction, right? So it's the petit morphisms are always a subcategory of the grow morphisms. So this is an extremely general construction.
What is intuition behind of absolute and relative definitions? As I understand, if we want to investigate some global properties, yes, we need to take absolute construction, yes, or if we need to investigate some local properties, we need to relate construction, yes, or it is not. I'm trying to find any intuition behind all these two definitions.
Well, the intuition will be sort of explained later, I guess, but in a sense that what we need to understand now is that the petit setting allows you to define only objects that locally look like objects in your site. Like something that locally looks like a Cartesian space, for example, which a priori excludes most examples. Most examples are excluded. But we do get to retain some very important examples like manifolds. And the difference between absolute and relative is simply that in the relative setting, you have a background space X, so to say, into which everything maps. In the absolute setting, on the other hand, you do not have such a space X. So that's the difference.
Thank you.
And let me maybe, so here I had a table of sites. Now let me give you a table of sheaves. What happens if you take sheaves on each of those four? So here is again grow empty, and here is absolute and relative. So in the absolute grow case, the sheaves will be, for example, something like smooth sets, which we already talked about in detail. In the absolute T case, you will see a subcategory of smooth sets, so stuff like manifolds, orbifolds, étal stacks, or if you work with algebraic geometry, you perhaps may see something like schemes constructed out of affine schemes. In the relative setting, if you equip everything with a map to X, then you will have, say, smooth sets over X. In algebraic geometry, this is extremely popular to do schemes over another scheme. This is like basically, in fact, they're sort of, that's how they do things by default. Everything is done over some fixed relative scheme. So in algebraic geometry, if you open any textbook, you are likely to see a lot of this relative psych stuff. They basically do everything in families. Family values are extremely important to them, I guess. And finally, and this moves us closer to our original goal of explaining traditional sheaves, they correspond to the relative Pti side. Let me explain this in a bit more detail. So in the relative Pti case, your objects will be, so you fix some, say, topological space X, right? X is a topological space. So we are talking about traditional sheaves over a topological space X. And your objects in your site will be open embeddings, or if you prefer, open inclusions of some U into X. So in other words, U is an open subset of X. And morphisms will be commutative triangles where all maps are open inclusions. So there is a morphism from U to V if and only if U is a subset of V, in which case there is exactly one such morphism. So altogether, the Pti relative psych is precisely the poset of open subsets of X. And as I said before, the Pti relative setting corresponds to the case when your objects are some kind of spaces that locally look like objects in your psych. And relative means everything maps into X. And of course, you can lawfully ask, what is the space over X corresponding to a sheaf of sets on this site open X? And according to our intuition, the space that corresponds to a sheaf of sets on this site should be a space that locally looks like an open subset of X, and it is equipped with a map to X. And indeed, that's exactly what happens. That's known as the so-called Étale space construction, or the displayed space construction. And the way it works, basically the category of sheaves of sets on X, which is simply the contravariant functor from open X up to set, satisfying the sheaf condition. This category is equivalent to a category with a purely geometric description. So this is an equivalence. So here you have what is called the Étale psych of X. So to say, objects in this category will be topological spaces E equipped with a local homeomorphism to X. So a local homeomorphism is a continuous map from E to X. It's a continuous map of topological spaces that such that E can be covered by some open cover, and from every element of that open cover, this map will be a homeomorphism onto its image. And morphisms between two such maps will be commutative triangles. And this map, this vertical map here, will be also necessarily a local homeomorphism, because local homeomorphisms have a 2 out of 3 property. So this map here is also a local homeomorphism. So I claim sheaves of sets on a topological space X are equivalent to this category. Here you can see precisely that what I said before, that the resulting spaces will be equipped with a map to X, and they will look locally, they will look like an open subset of X. And that's precisely what I just mentioned, that locally on E, this map is just an inclusion of an open subset into X. So how exactly does this equivalence of categories work? If you have such a Cal map from E to X, let's call it P, you send it to the pre-sheaf of sets on this site, whose value on some, and maybe here I should be a bit more precise, on some U, which is an open subset of X, will be simply what is called the set of sections of P over U. And more formally, this will be just continuous maps from U into E that make this triangle commute, which simply means you have a section of this map P, but not over X, but rather over a subset of X. And in case you are curious about the functor going in the opposite direction, that's known as the tau space functor. If you have a pre-sheaf of sets, you can construct this tau space. Maybe the easiest description is that points in the tau space will be what is called stops in your pre-sheaf, meaning a stock at some point is an equivalence class of sections over a neighborhood of this point, where two sections are identified if their restriction to a smaller neighborhood are equal. So here points are stock of F. But perhaps in a more sort of geometric way, to specify a functor from a category of sheaves, like this functor here, it's enough to define it on representables, meaning in our case, open subsets of X. And on representables, it's clear what to do because an open subset of X is clearly also an object here. It maps to X via a local homeomorphism. Okay, so I think this should explain the sort of perhaps any possible confusion that you may have had. So traditional sheaves are defined on the T relative side of a topological space X, whereas smooth sets are defined over the Rho absolute side of Cartesian spaces. The two may look different, but ultimately it's exactly the same ideology and the same technology that we use to define both. Any questions?
Construction fits into the adjunction we talked about between the slice category, for example, and
Yeah, of course. Yeah, so there are maybe I should mention a couple of comparison functor, right? So yeah, so let me just mention it on this page. So first, any petit psych including the corresponding growth psych, which means in particular you have a restriction functor, a sheaf on the growth psych, and a sheaf on a petit psych. They are related by well, I guess in our case it will be an at least an adjoint pair, right? The left adjoint and the right adjoint. And the left adjoint is easy to describe. It sends a sheaf on the petit side to a corresponding sheaf on the growth side. And basically this, in many cases, you can expect this to be a fully faithful an inclusion of categories which will be faithful but not full. So its image, the image of L, can be roughly described as some kind of the subcategory of egal stacks and egal maps, meaning inside of, say, smooth sets, you have very special smooth sets called egal stacks, which locally look like a Cartesian space. And you also have very, very special maps of such stacks, which are egal maps. Egal maps are basically maps that locally look like an isomorphism or homeomorphism or diffeomorphism, depending on your category. So this subcategory is not full, and this functor is not essentially surjective, but it is otherwise a nice subcategory. Yeah. The functor R is much more weird, but however, it has its uses in functorial field theory. For example, it ultimately plays a very important role in higher parallel transport, for example, because the petit cycle will be the cycle of d-dimensional manifolds and open embeddings. The growth cycle will be the cycle of all, say, Cartesian spaces in arbitrary smooth maps. And the functor R will be basically what is responsible for higher parallel transport. But let me not talk about this right now. I will be happy to explain it to you when the time comes. So that's one comparison functor. And the other functor is the forgetful functor from the relative side over x to the absolute side. This functor simply takes an object in a relative side, so something like u mapping to x, and it simply sends it to u. It forgets the map to x. And yeah, this also induces an adjunction, so sheaves on the relative side over x will map to via a left adjoint to sheaves on the absolute side. And there is a right adjoint. But the left adjoint again is more interesting. That's precisely the functor that forgets. It is a functor that forgets the map to x. So just forget the map to x. And the right adjoint will basically take, I think, the product with x. I think. Does this make sense? I think it should make sense, yeah. So it takes a product with X, and this product is equipped with a projection map to X, and that's how you get a sheaf on the relative side. To return back to this nice, let me keep this here and instead here. We can see how all those embeddings work. So the Petit integral gives you an embedding of smooth manifolds and orbifolds, Étale stacks into smooth sets. And of course, you also have the corresponding embedding. So traditional sheaves over X, these are given by a topological space that maps into X, that maps to X via some Étale map, via some local homeomorphism. And you can forget the fact that you have an Étale map, and you just have an arbitrary continuous map, let's say, and this gives you an inclusion here. And of course, you can also forget the map to X. So this gives you a forgetful functor like this. For example, you can take a traditional sheaf over X, forget, take as Étale space, which will be a topological space with a local homeomorphism to X, and you can forget the map to X. You just get a topological space, which is the analog of manifolds or orbifolds for topological spaces. Or, for example, you could have taken a traditional sheaf over X, where X is a smooth manifold, right? Then the Étale space would be another smooth manifold with a local diffeomorphism to X. It would be what is called an Étale stack mapping into X. And then the forgetful functor would simply extract the underlying Étale stack from this displayed space. Yeah.
Manifolds are Hausdorff.
Here, the display space will be almost always non-Hausdorff.
Right.
Should have mentioned this probably somewhere, because of course you typically would expect. So typically non-Hausdorff. In fact, it's also non-paracompact. In many cases, at least. So it's a manifold, but without the usual conditions. So if X is a smooth manifold, then its Étale or space construction will produce a manifold in the relaxed sense. So not Hausdorff, not paracompact, but otherwise something that has a charts and atlas of charts, and the usual conditions are satisfied. Okay, any more questions? Anybody wants to write up this lecture, by the way? I think we now have somebody. Let's see, I think Emilio is writing up something. Let's see. Okay. James wants to write it up. Okay. Or is it James? Who sent this message? Is James still here? No, James already left. I think that was James's message, right? So anyway, yeah, so if there are no more questions, then I guess that's it for today. And thanks for coming, for showing up. Let me stop sharing my screen.
Thank you for the lecture. Bye-bye.
Bye. All right. Should I now end the meeting, I guess? Let's see.